So this is work I've done with a bunch of collaborators at University of Washington: Brandon Holt, Brandon Myers, Preston Briggs, Luis Ceze, Simon Kahan, and Mark Oskin. So I'm going to start the talk 25 years ago, which Keynote has crashed. Isn't that fun? Try that again. Yes, absolutely. It looked exactly like that. Yes, we had three things going on in Seattle at that point. We had grunge music, we had plaid shirts, and we had a houseboat which was in a movie which wasn't really about our city, but everybody associates it with our city. So that's unfortunate, but okay, because what we want to focus on right now is what was going on in this community, in the systems community. There were a bunch of people exploring this really interesting abstraction, that of distributed shared memory, whose goal was to take a network of computers with independent address spaces and let people program them as if they were a single large multiprocessor machine. This was a great attractive model because we hoped that we could take the lessons we learned from writing code for a single machine and scale it up to a cluster. And so when we look at what these DSM systems looked like back then, we see that they were generally built trying to scale up the same techniques that we'd been using to get performance out of single nodes. In particular, they were designed to exploit locality. It was a common set of design choices to build caches using the DRAM and to use the paging hardware of the CPU to optimize for cache hits and make access to these caches transparent and fast, which was great, except that there was a consequence. This meant large cache block sizes, which meant performance problems with false sharing and synchronization. And so there was a bunch of interesting work that explored how to get around these problems. But what it meant is that the applications that worked really well on this platform tended to be sort of traditional HPC things that were compute-focused, were dense applications, were coarse-grained, not, in my opinion, the most exciting applications, but then I'm presenting this talk. So what we're excited about today, as we come back to the present, are things that focus more on data, things that we find in social network analysis or machine learning or bioinformatics, things that we refer to as data-intensive applications, because the data access here is the hard part. Often there's very little computation per data access in these applications, and locality can be hard to find, whether that's due to doing a natural graph traversal or a big join between a bunch of tables. So these applications are a bad fit for that traditional approach to DSM. And so our community has explored a bunch of different abstractions. And the point of this work is to pick up that abstraction of DSM again and see if we can find a way to make it work for these applications. The system we've built is called Grappa. And what we're trying to do with Grappa is to build a low-level piece of infrastructure that can support a diverse range of execution requirements, can support requirements from all kinds of data-intensive applications, in the hope that somebody building the next great data-intensive application framework doesn't have to start from scratch, doesn't have to optimize all the way down to the POSIX API. So this is a great goal, but it's challenging for a couple reasons. And so I'll talk about three of those challenges here. We'll start with this lack of locality. Now, sure, some data-intensive applications have locality, but if we want to be general, we need to support the worst case, and that is no locality, essentially random access. And in distributed shared memory context, lack of locality means lots of communication, and communication means network latency. We have great low latency networks now, but it's still a request-response round trip is hundreds of thousands of instructions on a modern CPU. Fortunately, these applications have a property which we can exploit to mitigate that latency, which is parallelism. There's all kinds of parallelism in the data. And so we can use that parallelism to hide this latency, to tolerate the latency. And I'll show you a simple example of how that can work. Imagine we have a task that's running on some core in our system. It needs to do a read of data that's stored on some other node in the system. Now, we might want to issue that read, if we were optimizing for latency, issue that read and then just wait for the response to come back. but we'll get much better utilization of the CPUs if we can context switch to other work, other independent work that we can pull from this big data set. Keep that CPU busy while we're waiting for the response to come back, then we can wake up the thread and continue. And if this was all it took to make distributed shared memory work for data-intensive applications, this would not be a super exciting paper. We have to look at why this is hard. And the big thing that makes this hard, in my opinion, is small messages. Let me show you what I mean. Here is the result of a simple ping-pong benchmark between two nodes in our InfiniBand connected cluster. I'm showing you the size of the messages we're pinging on the x-axis, and I'm showing you the effective bandwidth that we get out of moving those messages on the y-axis. And what we see here is that we've got great bandwidth if we're moving kilobytes of data. Unfortunately, in the data-intensive application frameworks that we've built on top of Grappa, we find ourselves moving 24 bytes of data. And on this network, that means that we get terrible bandwidth utilization out of the network. Now, there are techniques that you can use to improve this. They often involve changing the whole system stack. We wanted to build something that would run on clusters that are deployed today. So we're going to take advantage of another observation about these applications, which is that our real goal is time to solution. We don't care about the latency of individual operations. We care about the overall computation. And so what we can do is look for opportunities that, like a metered on-ramp to a freeway, allow us to get overall better performance, even if that means slowing down some of the individual operations. We use this idea in a bunch of different places in Grappa for communication, for synchronization, and for building data structures that can scale. The communication one is the most important one, and so I'll show you a simple example of that. So again, we have a task that's doing a remote read, but in this case, rather than issuing that read onto the network as soon as we generate it, we'll context switch to other work. We'll buffer that read and let other work happen in the hope that we'll find other remote operations that also need to execute on that remote node. And once we've waited for a while, we can find enough of those to build a large message out of these multiple small messages, move that over the network, and get good efficiency out of our network usage. Now, again, there's a consequence to this, and that is that now we have to tolerate the latency of the movement over the network, but we also have to tolerate the latency that we've created by waiting for these operations to accumulate. And so in our system, we find ourselves needing something like 500 to 1,000 threads running in each core in the system to tolerate these combined latencies. And so that leads us to the third item on the list, which is task granularity. These operations often have very little execution to do. We're sort of generating another remote reference, waiting for it to come back, doing a tiny amount of work. And so if we can't context switch efficiently, we'll find ourselves spending all of our time in the scheduler and no time doing useful work. So to make these two ideas work, we need fast context switching. And so the third piece, the piece that sort of enables all the other stuff that we do in Grappa, is a very efficient user-level cooperative multi-threading layer. Now, there are lots of these out there. What makes ours interesting is that we've optimized for this 1,000 thread per core case. In that case, even though we squeeze down our contexts and everything, we can't fit all of those contexts into an L1 cache. We know that we're going to have to move data into that cache somehow. So we can either pay the cost of misses in that cache, or we can do what we've done and build the scheduler such that it prefetches the context into the cache before we context switch to them. That lets us context switch at the DRAM bandwidth limit rather than the miss latency limit. And so that means that at this sort of 1,000 thread operating point, we can usually context switch in about 50 nanoseconds. So these three techniques are great, are important in making Grappa work. Now I want to tell you how we use these techniques to actually build the distributed shared memory abstraction. We do a couple things differently than what we saw in traditional distributed shared memory implementations. The first one is that rather than trying to make distributed shared memory a transparent abstraction, we actually expose it to the programmer as a language feature. Grappa is implemented as a C++11 library. We ask the programmer to expose parallelism with parallel for loops and with spawns, and to explicitly allocate and access data in this global address space. And so here's a very simple example of a recursive tree traversal On the top, I'm showing you standard single node code. On the bottom, I'm showing you the parallel Grappa version of that code. The differences are not important here. You can look at our paper or go check out our code if you want more details. But the point here is that with these small changes, we're able to have performance that scales in this graph up to 64 nodes of our cluster. So that's the first thing that we do differently than traditional distributed shared memories. The second thing that we do differently is the way we build the global address space. So you might imagine that given a cluster of multi-core nodes, we just sort of glue together all of the DRAM in all of those nodes. And within a single node, let those cores contend for access to this DRAM. We actually find it more efficient to partition things at a finer granularity. We'll take the DRAM in each multi-core node and we'll partition it across all of the cores and give each core exclusive access to one of those regions. Any sharing, whether within a node or across multiple nodes, has to be done with communication. So we add latency with that communication, but it means that all synchronization problems simply turn into scheduling problems. There's a third piece that makes remote memory access work in our distributed shared memory implementation, and that is a concept we call delegation. So delegate operations are essentially RPC with a little bit of synchronization so that we can build a sane memory consistency model around them. And I'll show you a simple example here. So we have a variable here which is in one of those partitions owned by a particular core, and we have a bunch of other cores that want to do atomic increments to that variable. Now in a traditional DSM implementation, we'd be running some sort of a coherence protocol between these cores, giving each one exclusive access in turn to increment that variable. In Grappa, as with some of the other talks in this session, we find it much more productive to simply migrate those operations, those increments, to the home core of that variable. And once we've migrated those operations, we can then stream through them with very low synchronization overhead and increment that variable quickly. And when this is combined with our ability to block on the requesting threads, it means that we can build a system that provides sequential consistency for race-free programs. So those are the pieces that go into Grappa presenting a distributed shared memory abstraction. Now I'm going to show you how it performs. And we'll start by looking at a very simple benchmark. Some of you may know this as GUPS or as HPCC random access. All it is a whole bunch of increments to random locations in a distributed array. It's just measuring random access bandwidth. I'm showing you pseudocode over here on the right part of the slide. And the graph is showing us performance on our 128 node cluster, which uses 32-core AMD Interlagos processors and Mellanox 40 gigabit InfiniBand. On the y-axis, I'm showing you the rate at which we can do these atomic increments, and the x-axis, I'm showing you the number of nodes. And I'm comparing two different implementations of this. So the green takes advantage of the fact that our network hardware has the ability to do atomic increments in hardware. So this is GUPS implemented directly with InfiniBand verbs. Blue is the Grappa version using delegation and aggregation to do these increments. And you see a big performance difference here. It's something like 25x. And I think what we're really taking advantage of here is that we're able to mobilize all of the cores in our platform to do these increments rather than depending on the network interface to take care of them. I should say that Grappa also uses RDMA to move data, but aggregated data, and it does so by building on top of MPI. So we still have portability to networks that use TCP, but we can take advantage of RDMA for moving our aggregated messages when is possible. Okay, so that's a really simple benchmark. Now let's look at some more interesting things. Our goal here is to provide a platform for building new data-intensive application frameworks. So to evaluate how well this works, we built a couple prototype frameworks. We built a simple in-memory MapReduce implementation, which we'll compare with Spark. We built a subset of the GraphLab API, which we'll compare with native GraphLab. And we built a backend for a relational query compiler, which we'll compare with Shark. And before I show you results here, I want to say one thing about metrics. it would be great. I would be perfectly happy if we simply had equivalent performance with these native frameworks, because that would say that the abstraction wasn't holding us back in implementing these frameworks. We end up doing rather better than that. So let's first look at our in-memory MapReduce implementation. This thing is optimized for iterative applications, and we didn't look at fault tolerance in this work, so when we compare with Spark, we disable its fault tolerance features. The benchmark we use is a simple k-means on an ocean flow cytometry dataset from the oceanography department at UW, running on the same cluster that I mentioned before. And here's the result. I'm showing you runtime normalized to Grappa on the y-axis, and we see that we're about 10 times faster than Spark. Now, there are various reasons for this. I'll talk more in more detail about those in a couple slides. But the point is that the abstraction is not holding us back here. It's actually helping us. Let's next look at the relational query execution backend. So this is a backend for the Reiko relational compiler, which takes queries in SQL or Datalog and compiles them down into various execution frameworks, one of which is Grappa. The compiler generates for loops, which we can then compile and execute on our infrastructure. We're comparing that with Shark running on top of Spark using the SP2 benchmark suite. And so now on the y-axis, I'm showing you normalized runtime averaged across all of the benchmarks in this suite. You can look in the paper for a breakdown of the individual benchmarks. We see a similar result to what we saw with the MapReduce implementation before. Now the performance difference is something like 12.5x on average. This is actually the most interesting of our comparisons, though, the GraphLab implementation. Because it's the same platform, it's also C++. So we have similar costs for serializing and moving data. We implemented a subset of the GraphLab API as described in the PowerGraph paper with one difference, which is that GraphLab works well because it has this really interesting graph representation which replicates data to try to exploit as much locality as possible, and it has a whole selection of partitioning schemes that allow it to do that. In Grappa, we just did something simple. We implemented a simple adjacency list representation for the graph with no replication and partitioned it randomly across our cluster. We'll compare this using 4 graph analytics benchmarks on 2 social network graphs. And again, I'm going to show you normalized runtime averaged over all of these benchmarks and data sets. And what we see here is that when we compare Grappa with its simple graph representation to GraphLab with its best partitioning strategy, we still end up being 33% faster. We're about 2.5 times faster when we compare with a random partition on Grappa, or on GraphLab, I mean. And so what's going on here? Well, the primary thing is just that Grappa is really good at moving small messages around the system. This is partially due to the fact that we've built our system to allow the use of RDMA, whereas Spark and GraphLab were not built for that perspective. But even when we use Grappa with TCP, we still find higher message rates. We end up doing very efficient message serialization as well because we can essentially take advantage of the data layout in memory. But higher message rates is not sufficient. We also need the fine-grained synchronization and scheduling to be able to generate and to process these messages. And you can look in the paper for a much larger analysis of what's going on here. So, before I conclude, I'll just mention a couple other things that I don't have time to talk about in the talk today. As I said, there's a deeper dive on performance. You can also see an example of programming directly against the Grappa API. We've done a bunch of other work to support this, including Alembic, which is a compiler pass that helps find and extract delegates from ordinary code. You can find more information on the relational query compiler in the Radish paper, and then there's another paper called Flat Combining Synchronized Global Data Structures that talks about how we build data structures that take advantage of latency tolerance on Grappa. And with that, I'll conclude. Grappa is a distributed shared memory platform for building new data-intensive application frameworks. It runs very quickly because of latency tolerance. We can actually trade off latency to get more throughput. And you can check out our website for more information and to take a look at the code. And with that, I'll take questions. Thank you.
Joe Duchek, HP Labs. I have a question about your implementation of the GUPS benchmark. So GUPS has, it's a benchmark, and so it has rules to keep people from like tweaking one little thing to an extreme extent. One thing that the benchmark authors recognize is that prefetching and aggregation gives a huge benefit for that particular workload. So they put limits onto how much is allowed. So I was wondering if you could speak a little bit as to exactly how much aggregation you're doing and whether or not that's compliant with the limits that the rules specify.
Well, so let's be specific. You're talking about HPCC random access specifically, right? There are many, many different implementations of GUPS that the NSA has asked people to build over the last 40 years.
Yes.
So we have focused more on that flexible framework. Here we're doing slightly more aggregation per core than probably what HPCC random access would allow. I don't know how many messages were in flight there, but probably something like 1,500 per core, where I think they limit to 1,000. So we could artificially limit our GUPS performance there, but the thing I think you should focus on there is that we're actually providing something better than what you get with many of the other GUPS implementations, that all of those increments are actually atomic, right? So sure, we can we're aggregating more than we need, but you're actually getting a precise result out of the other end of the system.
Thanks.
Quick question. In this slide where you talked about why Grappa is faster, you mentioned RDMA and other optimizations. I'm just curious if there's a breakdown that you have of how much RDMA contributed to the improvement versus other optimizations.
Yeah, let's see if I have that slide somewhere here. Didn't want to spend too much time talking about that, but since you asked, I will pull that up. So the graph to focus on here is in the upper left. So what we did is we implemented GUPS using GraphLab and Spark's native communication layers as well. And then we have two Grappa implementations, one using TCP, the other, so that's IP over InfiniBand, and the other using the native RDMA. I'm also showing some message prefetching there, enabled and disabled. And so there's, a factor of 2 performance difference when we are able to use that RDMA capability. But you can see that the other features that we're including there still allow us to perform quickly there.
I just have a quick clarification. What were the data sizes that you considered for the like the Spark benchmark? And like, to what extent does this thing scale over, let's say, conventional stuff?
Yeah, so we built the system intending to focus only on the in-memory subset of data-intensive applications. That said, the data sizes that we used in the evaluation are fairly small. They could certainly fit in a single node, and I think this is a weakness of a lot of work that's been done in this space in recent years, especially when we start looking at graphs. It's hard to find graphs that are large enough to actually make it worthwhile scaling up on a cluster. But capacity is not the only thing we want to, think about here. There's also the bandwidth question, and we're able to take advantage of more bandwidth as we scale up to multiple nodes.
Russell Lewis, University of Arizona. I was curious about the fast context switching. So you were prefetching cache lines, and you said you needed one cache line for the state. I'm assuming that's not enough to hold all the registers, or am I mistaken there? We
use a trick that is common amongst these cooperative multithreading packages, which is to take advantage of the ABI. There's only a subset of registers that need to be, I'm confused now, callee saved, I think. And so we're essentially just saving those registers and depending on the compiler to spill any others to the stack before we context switch before that.
Oh, thank you.
Mm-hmm.
Sorry, so I get that fault tolerance is outside the scope of this work, but 128 nodes is a lot of nodes. And I'm wondering if you could offer any sort of speculative thoughts as to how you would start tolerating failure at the node level and at lower granularities as well.
Sorry, could you ask the second part of your question again?
Oh, I mean, you could imagine smaller granularities than node, but node is probably interesting enough at 128.
Yeah. Yeah, I mean, I think there are a bunch of things we could do to support fault tolerance. The easiest would probably be some sort of chain replication strategy, because that's essentially just adding more latency to the latency that we're already covering. Great.
Thank you so much.